Alright, in the next few minutes I want to look at some bizarre graphs. No, they're not even really graphs. I would call them diagrams. Kind of a graphical organizer trying to relate solid, liquid, gas for a particular substance into categories based on some correspondence of temperature and pressure. But since the axes aren't linear, I actually rarely call these, rarely call them graphs. I think they're more like diagrams. Is my program going to work here? I was trying to... No, don't do that. I was trying to get larger. Oh, there we go. So, it's a nice one here because it shows me or reminds me the solid, liquid, gas particles. This is for ice, actually, for H2O. Ice, liquid water, gaseous water. The molecules would even be a little bit further apart. But if I put pressure on the y-axis, on the y-coordinate, temperature on the x-coordinate, I don't know if I want to call them axes because they're not linear for sure. I remember solid, liquid, gas. If I have a 0-degree temperature sample at normal atmospheric pressure, I get what I call the normal freezing point of water. And anything colder than this or at this pressure, would be a solid. But I suppose it's possible to have such a low pressure like in outer space on a sample of ice, and it actually changes from a solid to a gas. This is the gaseous region here in white. Or if I have, say, room temperature water and normal air pressure, it's certainly a liquid. But I could, again, lower the pressure on that liquid. If I was, say, right here on the diagram, and I kept the temperature constant, but lowered the pressure, I would move down the diagram to this point where I would see, interestingly, the water, quote, boiling, because there wouldn't be enough air pressure on top of it to keep it into the liquid phase, and then eventually I could boil the entire water sample into a gas phase. There's a couple of good points to think about. There's something called the triple point. Let's ask ourselves, before we talk about that, let's ask ourselves what each point on this line from here to here means, what each point on the line from here to here and beyond means, and what each point on the line from here to here and beyond means. Well, what if I was sitting right on the intersection of solid and liquid? You know what that's called, yeah? It's called melting or freezing, depends which way I'm removing or adding heat. So if I had a sample right here on the temperature pressure correspondence, I would have a mixture of solid and liquid. Some of the solid would be melting into a liquid, some of the liquid would be freezing into a gas, seemingly at random or coincidence, happenstance. Equilibrium is what we call the situation. Each point on the curve represents an equilibrium situation between two phases of matter. If I was at this position right here, I'd be a mixture of liquid and gas. Or indeed, if I had a boiling pot of water on the stove, I would have some liquid and some gas. And down here is kind of even a more unusual situation, but you notice the pressure is pretty low. It's lower than 5 millimeters of mercury. At very low pressures, I can have mixtures of solid and gas. But what about this triple point thing? Well, as its name describes, triple means 3, and solid, liquid, gas, I'd have all 3 phases mixing and mingling, melting and freezing, and boiling and condensing, and subliming and depositing at random. And it would seem that on a molecular scale, it would seem that I would be really confused because the particles could do whatever they wanted to do if indeed I held it right just a little bit above freezing and very, very low pressure. Maybe in lecture I'll give you a video demonstration of that triple point. It's actually pretty hard to do to keep the conditions just right so that we can notice that. This is a one for carbon dioxide. You may or may not notice a difference. There's a very subtle but very important difference. You see, most substances have this equilibrium line between solid and liquid with a positive tending slope up and from down left to up and right, as is also the slope from the liquid gas equilibria or the solid gas equilibria. Most substances have positive slopes, but if I check back up here, I see that's a negative tending slope, which is kind of confusing. It's a consequence of water expanding when it freezes, and solid ice floats in liquid water, which is very rare for most substances. Most substances have their solids sinking in their liquid. Notice the triple point's different for carbon dioxide. The triple point's different for every different substance has a different triple point. But there's a new point we added up here called the critical point. The critical point is the temperature above which the gas cannot be compressed into a liquid, no matter what the pressure. It's not hard to compress a gas into a liquid with enough pressure, but there could be a temperature so great that you cannot do that. You have what's called a supercritical fluid. Yeah, again, demonstration in class, I hope. That's all. Yeah, that's enough of that for now. Again, notice the water has the backward tending slope on the equilibrium line between the solid and liquid. You can draw it many different ways. I don't know who authored these diagrams, but they're all legit. Melting point, normal boiling point, sublimation point, perhaps? I don't know what SP stands for anyways. I know sublimation is from solid to gas. I just guessed at that one. So it's really hard to read numbers off of a phase diagram. Really hard or impossible unless you're given the numbers. Triple point temperature, triple point pressure. Unless you're told exactly what these numbers are. Since the axes are not linear, it's really hard to read the axes. But you should remember the general solid, liquid, gas. Good also to know that the line for water between solid and liquid slopes backwards. Supercritical fluid beyond the critical point. You should know that. Yeah, and equilibrium. Interesting idea is that each point, this point and this point and this point and this point, all describe an equilibrium condition for a sample of, be it water, be it anything, where I have mixtures of those two phases changing almost at will, I suppose. Just another one for water. Cold glass of ice water, boiling pot of water with the lid on the stove, 1 atmosphere pressure, 100 degrees and 0 degrees. You know, freezing and boiling of water is what the Celsius scale is based on originally. Under Celsius, some French dude, I think, back in the Renaissance, came up with a scale. Yeah, whatever. Okay, more of the same. Oh, here's an interesting one I wanted to point out. Oftentimes in equilibrium we'll see the double arrows. So I don't mean to say I'm moving from here to here. I'm saying if I'm sitting right on that point line, the equilibrium line, I might have some melting and I might have some freezing in the same container in the same time with neighboring particles. As confusing as that might be, it's true. What if I had a sample of ice or snow at 0 degrees or a little bit below 0 degrees even, and well, then of course in the air it's frozen. If it's below 0 degrees, it freezes into snow or ice. But then you start to walk on the ice, or you ski on the ice, or you drive on the ice, or your grandma comes to visit you for Thanksgiving. She walks on your icy sidewalk. You better get that cleared off. But as pressure from a foot, from a ski, from a snowshoe, from a tire, car tire, when the pressure is increased on that snow because someone's standing on it or a car is driving on it, as the pressure increases, the temperature stays the same, but can you tell what happens to the phase? So up here I've turned into a liquid. Down here I used to be a solid. So if by increasing the pressure on some snow or ice, I can melt it from a solid to a liquid, what that does is creates a very small micro layer of liquid between the solid and your foot or the tire or the ski, and of course that liquid layer is very, very slippery between your foot or the ski or the car tire and the other still frozen sample. Oh, yeah. I think that's just about. I have some other interesting diagrams. That's the gist of everything here. Um, Decrease pressure. So if I had a liquid again, and I decrease the pressure but kept the temperature the same, I can boil it. Very interesting. Let's see if I can set that up for you. I don't know if I can. Maybe. Uh, with very extreme temperatures and pressures, you can see really bizarre phase diagrams. Don't remember any of these, besides they're kind of blurry, but I snipped them off the internet. The point is, there are actually several different kinds of phases of ice or diamond or any substance. Iron, this is for iron. It's a phase diagram for some funky pressures and temperatures on iron, and some folks that study these phase changes have noticed many different things other than just simple solid, simple liquid, simple gas. Wow, here's one for graphites and diamonds. You can have liquid carbon or vapor carbon. Interesting. Alright, let's stop there, guys. Thanks for your hard work, and I'll see you soon.